Let's take a look at AP Review 4 today. Problem number 1, a car travels on a straight track during a time 0 to 60 seconds. The velocity is measured in feet per second, acceleration is in feet per second. They're both continuous functions. The table above shows selected values. Use appropriate units to explain the meaning of the integral from 30 to 60 of absolute value of v dt. Well, absolute value means I'm going to take this graph and turn it into this graph and then integrate. All those negative bits become positive bits. So when I integrate, I get total distance. So this is total distance traveled in feet from 30 to 60 seconds. Approximate the value of this using a trapezoid sum with 3 subintervals. Okay, so we want 1/2. I notice that the subinterval widths are not the same, so I can't use the shortcut. I'm going to do 35 minus 30 times, and we're looking for total distance traveled, so we want negative 14 plus. Oh, no, we don't. We want the absolute value. We want positive 14 plus 10. Okay, and then the second trapezoid, 1/2. I guess we could have pulled the 1/2 out of everything. Let's do that. 1/2. And then here we have 50 minus 35 and 10 plus 0. And then our last trapezoid, 60 minus 50 times 0 plus 10. Close bracket. Okay. So if you're wondering what the value of that is because you actually computed it, I got 185 feet. But I think you should just leave it here on the AP exam and not risk losing a point for simplifying wrong. Okay, part B, use appropriate units to explain the meaning of 0 to 30 of a of t dt. Well, that's going to be the same as v of 30 minus v of 0 when I use FTC part 2. And we know this is the change in velocity from 0 to 30 seconds. Okay, do they want us to figure it out? Find the exact value of this. Oh, well, I just need v of 30, which is negative 14, and v of 0, which is negative 20, and so I end up with 6. And the units here are velocity units. These are feet per second. We want 6 feet per second for part B. Okay. Oh, I didn't get a wiping towel. Okay. So let's take a look at what they want in part C. Part C says 0 to 60, there must be a time when V equals negative 5. Well, I would say that since V is continuous according to IVT, V must pass through all the values from V of 0 equals negative 20 to V of 60, which equals 10. And so passing through all the values from negative 20 to 10, therefore or I must pass, or velocity must pass through v equals -5 on that interval. Okay, and part D, when a of t equals 0, a of t equals 0. Okay, so if a of t equals 0, I'm thinking about a of t represents the slopes of v, and so I'll say since v is both continuous and differentiable, according to MVT, there must be at least one point t equals c such that a of c if c equals the integral from 0, no, that's not it at all, sorry, a ver, where there we go, v prime equals a is v of b, let's go with, yeah, b minus v of a over b minus a. So I'm looking for when the average rate of change is equal to, I want this to be equal to 0. So that would mean, are there two velocities that are the same? And I see two velocities that are the same on 0 to 25 seconds. So v of 0, v of 25 minus v of 0, 25 minus 0 will be equal to 0. So since there is a moment when MVT is true on 0 to 25, it must also be true on 0 to 60. That's not elegant. I look forward to your more elegant write-ups than that one. Ew, that was not nice. Okay, and I think I need to move the camera down slightly. All right, so that was number one. Number two, Ben rides a unicycle back and forth along an east-west track. Actually, I have a high school friend who does off-road unicycling. No, really, those people are out there. Twice differentiable function b models Ben's position. So the derivative of b will be Ben's velocity. Table above gives values of b and v. The units are meters and meters per second. Use the data to approximate Ben's acceleration. Now notice it says approximate Ben's acceleration at 5. Well, I know that the definition of acceleration is average rate of change in velocity with respect to time. So average acceleration will be v of b minus v of a over b minus a. Okay, so if I want to know at 5, I can approximate, or I can say acceleration is is the rate of change there. That's what I wanted to say. Acceleration is approximately the average rate of change in velocity with respect to time. That's going to give me exactly average acceleration, but I can approximate acceleration with this as well. So what do I get when I do at 5? Well, I'm going to say v of 10 minus v of 0 over 10 minus 0, and say that's 2.3 minus 2 over 10, or 0.3 over 10. And I need some units, which I guess is 0.03 meters per second on top. That's what these are. And these are seconds on the bottom. So 0.03 meters per second is what we're looking at there. Okay. Part B. Use correct units to interpret the meaning of this. Well, we saw this in the last problem. 0 to 60 absolute value of v is total distance traveled in meters on 0 to 60 seconds. And do they want us to figure it out? Yes, they want us to use the left Riemann sum to do this. This is the sums packet, so I expect to do sums everywhere. Total distance traveled. If I'm looking for the total distance traveled, I'm integrating velocity. So subinterval width 10 minus 0 times the left side 2 plus 40 minus 10 times the left side 2.3 plus 60 minus 40 times the left side 2.5. This is without calculator. I would probably recommend that you leave it here, but if you really can't help yourself, you should get 139 meters when you actually go through that and figure it all out. Okay, what about part C? C says, must there be a time t when Ben's velocity on 40 to 60 is 2 meters per second? So, if I think about velocity must be 2, I can't use IVT because I don't see any numbers below 2, but can I use MVT? So I know that V equals B prime, and I know that there must be some point where B of B minus B of A over B minus A. According to mean value theorem, since B is continuous and differentiable, they tell us that in the stem of the problem, MVT says there must be a time on, our interval was 40 to 60, when, well, let's check out what is B of 60 minus B of 40 over 60 minus 40. Well, I get B of 60 is 49, B of 40 is 9, and I get 20 here, and so I get 40 over 20, or 2. As if by magic we got exactly the rate we wanted, and therefore B prime at some point, also known as V at that point, must be 2. So there must be a time on 0 to 60 when V equals 2 because of this stuff. Okay, and finally part D for number 2. A light directly ahead above the western end of the track. Um, light. Um, Rides so that the distance L between the light and Ben, light, satisfies this equation. So B12 L. L? Yes, L is the hypotenuse. Okay. At what rate is the distance between Ben and the light changing at t equal to 40? So we want to know dl dt. And we can just do a related rates problem from chapter 5. We'll say 12 squared plus b squared equals l squared. And then we'll take the derivative everywhere with respect to time. The derivative of this is 0 because it's a constant. The derivative of this is going to be 2b, but don't forget to take the derivative of that inside b function with respect to time, also known as db dt, and that should equal 2L times dL dt. Remember that dB dt, that's the change in Ben's position with respect to time. That's also known as his velocity. Okay, and we want to know at t equal to 40. So Ben's position at 40 is 9. Ben's velocity at 40 is 2.5, or 5 halves. And then we've got a 2 here. L. Since we know that this is 9, I see a 3, 4, 5 right triangle. This must be 15. I'm going to need to find that to put it in there. 15 and dl dt. So then dl dt is going to be, these 2's cancel, 45 divided by 30, or 3 halves. And I guess we should put some units here. These are meters per second. Okay, there's part D for problem number 2. Let's move on. See what problem number 3 looks like. Problem number 3 says a pot of tea cools. Temperature is modeled by H. Okay, so we've got this H function for the heat of the temperature of the tea on 0 to 10 minutes. Selected values are shown in the table above. Approximate the rate at which the temperature of the tea is changing at 3.5. Oh, well, I don't have 3.5, but I can approximate this by saying h of 5 minus h of 2 over 5 minus 2. And so that's 52 minus 60 over 3, which is negative 8 over 3. The units up here for H are degrees Celsius, and the units here on the bottom are minutes. We've got degrees Celsius, and we've got minutes. Okay, what else? Oh, and this is approximately H prime at 3.5. What about part B? Part B says, using correct units, explain the meaning of 10 integral 0 to 10 of h of t dt. Well, this is, 1 over b minus a integral a to b of h of t dt. We know that's the average value of h on 0 to 10. And so in our problem, it's the average temperature of the tea in Celsius degrees from 0 to 10 minutes. Do we need to compute that? Yes, they would like us to use the trapezoid sum with 4 subintervals. indicated by the table to approximate this. Now, many people, when they do this problem, they do the trapezoid sum beautifully. Like they just do a perfect trapezoid sum. And they don't get the answer point because they forget the 1/10 out in front. So let's put that 1/10 there, and then the 1/2 for our trapezoid sum. The subinterval widths are again not the same, so I can't use my shortcut. So I'm just going to do 2 minus 0 times 60 plus 66 plus 5 minus 2 times 52 plus 60 plus 9 minus 5 times 52 plus 44 plus 10 minus 9 times 44 plus 43. Again, don't forget that 1/10. And again, I don't think I would take this any further. You're just going to be wasting a lot of time and risking making a small mistake. But if you do, you should end up with 52.95 degrees is the average temperature of the tea in degrees Celsius on 0 to 10 minutes. Okay, so that was part B. Part C, evaluate this. Okay, part C says integral 0 to 10 of h prime of t dt. Well, I know the fundamental theorem of calculus says that this would be h of 10 minus h of 0. H of 10 is 43, h of 0 is 66, and so I get negative 23 degrees Celsius. This is the change in temperature in degrees Celsius from t equals 0 to t equals 10 minutes. Don't forget, this is important. The time is important. It's not just the number negative 23. Please make sure you give a full explanation of this. Okay, part D. Ooh, now we've got biscuits. At t equals 0, the initial temperature of the biscuits, B of 0 was 100 degrees Celsius. And we have this b prime function, which is negative 13.84 e to the minus 0.173 t. And we know that if we integrate b prime from 0 to 10 dt, that's going to be b of 10 minus b of 0. Well, I know that b of 0 is 100, so I'm going to do this integral on my calculator because it's a calculator portion, and I'm going to add 100 degrees to that to get b of 10. So I'll pull out my calculator, and I'm sorry I don't have a glowing screen. Someone stole that calculator, so I don't have it anymore. But I can certainly type in this function, negative 13.84 e to the negative 0.173 t. Okay, so I've got this function here. I go back to my main screen and I do fint y1 comma x comma 0 comma 10. There's the change in temperature of the biscuits. We add 100 degrees to that. And so at time equal to 10, the biscuits are going to be 34.183 degrees Celsius. It says how much cooler are the biscuits than the tea. We know that the tea is at time equal to 10, h of 10 equals 43 degrees. Biscuits at 10 are 34.183 3 degrees. And so if we do a little subtraction on our calculator, I get 8.817 degrees Celsius cooler. Biscuits are cooler than the tea at time t equals 10 minutes. Okay, there's number 3. Let's take a look at number 4. 4 says, scientists measuring the depth of the Doe River at Picnic Point. The river is 20 feet wide at this location. Straight line perpendicular to the edge of the river. The data shown, okay, distance from the river's edge. So what we're saying is that this river is 24 feet wide. And if we go out to 8 feet, the depth of the river is 7 feet. And if we go out to 14 feet, the depth of the river is 8 feet. That's what they're telling me here, okay? Just so that you have an understanding of what's going on with all this language. Sometimes that can be helpful. And we've got the velocity of the water given by v of t on 0 to 120 minutes. Use a trapezoid sum with 4 subintervals to indicate the approximate area of the cross-section of the river at Picnic Point in square feet. Okay, so, and they said trap sum, so I checked to see if the subinterval widths are the same. They're not, so I can't use my shortcut. Instead, I say 1/2, and then the first trapezoid, 8 minus 0 times 0 plus 7, and then the second trapezoid, 14 minus 8 times 7 plus 8, and then the third trapezoid, 22 minus 14 times 8 plus 2, and finally the fourth trapezoid, 24 minus 22 times 2 plus 0. Again, I would leave my answer like that, but if you're a glutton for punishment, you should end up with, oh, and they did want feet squared, so don't forget that if you leave it in this form. You should end up with 115 feet squared as the cross-section of the river. Okay, part B. The volumetric flow is the product. Okay, so flow is the product, so I'm going to be multiplying two things together. The product of the cross-sectional area. Oh, I just found that area. Cross-sectional area times the velocity of the water at this location times velocity. Okay, so then I'm thinking about reading further. Use the approximation from part A to estimate the average value of flow. Okay, so I want the average value of this. Average value on 0 to 120 would be this integral 0 to 120 of f dt. Okay, so what we're going to do is we're going to do the same thing, but we're going to first realize that this is our constant 115, and we'll pull that constant out, and we're going to integrate v. So 115 over 120 integral 0 to 120 of v dt. This problem is with calculator, so I'm definitely pulling out my calculator, typing in that v function, 16 plus 2 sine square root x plus 10, close two parentheses. Okay, and I'm going to check to make sure that my mode is still in radians. Good. I go to math, integrate. I want the function in y1, comma x, comma 0, comma 120. And don't forget, I need to multiply this by 115 over 120 times 115 divided by 120, and I end up with 1807.170697. We'll round to 170 cubic feet per minute. Because this is going to be giving me cubic feet. Velocity is feet squared per minute times that number. No, volumetric flow tells me it's cubic feet. But now how do I chase the units here? I know this is feet squared, and I know that these are minutes. And so what I get when I integrate velocity is feet. That's it. So feet times feet squared is feet cubed per minute. Great. Okay, so there's part B. Part B. Do we need to do anything else there? No. Part C. Don't be intimidated when they do things like flow is the product of cross-sectional area and velocity. Just go slow and write it out and translate from math to English. Okay, or from English to math. A scientist proposes a function f of x, which is 8 sine pi x over 24 as a model for the depth of the water at Picnic Point. Find the area of the cross-section of the river at Picnic Point using this model. Well, I think we just want to integrate across the width of the river. I'm going to pull out my constant, sine pi x over 24 dx, and this is with calculator. So I'm just going to integrate this on my calculator and get 122.231 square feet. Okay, part D. Recall that volumetric flow is they really want to use this. The product of the cross-sectional area and the velocity at the point. To prevent flooding, the water must be diverted if the average value of volumetric flow, weren't we finding the average value of volumetric flow? Yes, we did. That's our answer to part B. If that average value exceeds 2,100 cubic feet per minute for a 20-minute period. Okay, so I'm taking that answer to I'm thinking about flow as the area times velocity. And we just found what the actual area is, not an approximation for area. So I'm going to use this number now. And we're still using the same v function, I believe. Yes. So, and we're doing this from 40 to 60 minutes. So I'm going to have 1 over 60 minus 40 times integral from 40 to 60 of 122.231 times the velocity function v of t dt. Okay, I can pull this constant out and then just integrate v of t from 40 to 60. I think I still have v of t typed in there. So 122.231 divided by 20 times math integral of y1, no, y1, comma x, comma 40, comma 60. And I end up with 2181.913 cubic feet per minute. this is greater than 2100. So the water, therefore, water must be diverted. Okay, there's 4D. Let's move on to problem number 5. Problem number 5 says blood vessel. Ooh, and this is with calculator too. Blood vessel is 360 millimeters long, okay, and has a circular cross-section of varying diameter. So blood vessel with a circular cross-section of a varying diameter. Okay, so that's what I'm thinking about. Now, what do they intend? B of x is the diameter. Write an integral expression in terms of b of x that represents the average radius. The average radius. Okay, so I know that radius is diameter divided by 2, so I want b over 2. And what would I like to do with that? Well, I want the average value of that b function, 0 to 360, of b over 2 dx. Okay, and they say that I should use the table of data. Oh, wait, that's the next problem. Write the expression. I've written the expression. I think I'm done with part A. This is part A. Part B. Approximate the value of part A using a midpoint Riemann sum with 3 subintervals of equal length. Well, 360 minus 0 divided by 3 is 120. So my first rectangle goes from 0 to 120. My next rectangle goes from 120 to 240. And my third rectangle goes from 240 to 360. Remember, when we're doing MRAM, midpoint Riemann sum, we want to go halfway across the interval and pick up that y value, or in this case, a diameter value. So I'm going to say then, oh, and look, the subinterval widths are all the same. So instead of doing 120 times 20 over 2 plus 120 times 30 over 2 plus 120 24 over 2. I'm going to say, hey, I can definitely pull out these 120 over 2's, and I've got this 360 out in front as well. So don't forget times 1 over 360. So I pull out the 120, I pull out the 2 on the bottom, and then we're left with 20 plus 30 plus 24. Again, you should probably leave your answer here, even here. I'm not keen to really risk the point, but if you do, you should end up with 14 millimeters is the average radius on 0 to 360 millimeters. Okay, so that's part B. Let's take a look at part C. Part C says, using correct units, explain the meaning of pi integral 125 to 275 b over 2 squared dx. Oh, well, this is pi radius squared. So this is going to be the volume of the blood vessel in cubic millimeters from millimeter 125 to millimeter 275. Okay, that's what that means. Do they want us to explain the meaning? Okay, I think I did that. Didn't I do that? Yeah, great. From on the length of the blood vessel. Okay. What about D? Explain why there must be at least one value on 0 to 360 where B double prime equals 0. Well, I think this is MVT, and since B is twice differentiable, we know that B double prime, I'm sorry, that B prime is continuous and differentiable. So, according to MVT, B double prime equals 0 if B prime at some point minus B prime at another point equals 0. And that would be true if these two were the same. So do we have any places where B prime is the same? So if I think about B prime being the same, I see I see, wow, this is sort of abstruse. Let's find maybe another way to do this problem. If I look at the table and see that B of 180 minus B of 60 over 180 minus 60, that could be used to approximate B prime. I get 0 for that. And then if I look at B of 360 minus B of 240 over 360 minus 240, then I get, lo and behold, 26 minus 26, or 0. So I do have two places where B prime will be equal to 0, and therefore B double prime must equal 0. That's a lot of explaining to have to do. Oh my goodness. I might suggest, um, I think that's the way they would like me to explain it. But, B double prime equals 0 is an inflection point on B, which is also or max or min on B prime. So do we change directions on B prime? Does B prime go from uh, does B prime go from increasing to decreasing or decreasing to increasing? Well, if I just think about B and whether or not it's increasing or not, it looks like on 0 to, maybe it's 60, maybe it's before 60, maybe it's after 60, B is increasing at first on that interval, and then B seems to be decreasing because we have 30 to 28. And then B is increasing again, 28, 30. And then B is decreasing. And that goes 26 to 24, but then we've got 24 to 26. Then B is increasing. So I've got increasing, decreasing, increasing, decreasing, increasing. Well, I can see, and this is a continuous function, so no pointy points here. These are all curvy things. So I'm going to have 0 slope, 0 slope, 0 slope, 0 slope. That's that other approach I was talking about. But let's think about inflection points. Between this max and this min, I have to have this inflection point because I'm going from concave down to concave up. And then I'm going to have another one over here. So I definitely have two places where B prime is undefined. B double prime equals 0. But that's a tough one. Oof, yikes. All right, problem number 6. Problem number 6 says temperature in water of a tub is modeled by a strictly increasing twice differentiable function W, where W is measured in degrees Fahrenheit after T minutes. T equals 0, the temperature of the water. W of 0 equals 55. I see that in the table. But I think they're telling me that here because I'm going to be doing FTC Part 2, and I'm going to need to use that, but we'll see. And then water is heated for 30 minutes, beginning at T equals 0. Values of WT at selected times in the first 20 minutes are given in the table. Use the data in the table to estimate W prime of 12. Okay, so for part A, W prime of 12 is approximately the slope between 15 and 9 and 15. So that's W of 15 minus W of 9 over 15 minus 9. Okay, and this problem is with calculator, so I pull out my calculator and I get what do I get? I get 6.1 over 6, or 1.017 degrees Fahrenheit. That's what's on the top. On the bottom we have minutes. So W prime of T, or the change in the temperature of the water at time equal to 12, is approximately 1.017 degrees Fahrenheit per minute. Notice this number is positive. That means the temperature of the water is increasing, and that's consistent with what they told us at the beginning of the problem, or in the stem of the problem. The temperature is increasing. Okay, part B. Part B says use the data in the table to evaluate 0 to 20 of W prime of T dt. There's our FTC2 problem, W of 0. So W of 20 is 71, W of 0 is 55, and I end up with 16 degrees Fahrenheit. And do they ask me to interpret the meaning? Yes, they do. The temperature of the water increased by 16 degrees Fahrenheit on 0 to 20 minutes. Okay, part C. The average temperature of the water in the tub is given by 1 over 20 integral 0 to 20 WT dt. That's the average temperature on 0 to 20 minutes. That makes sense to me. Okay, what do you want me to do with that? Use a left Riemann sum with 4 subintervals to approximate this. Again, don't lose that constant. 1 over 20. Left Riemann sum. The subinterval widths are not the same, so I'm just going to need to do the area of 4 separate rectangles here. I've got 4 minus 0, and I've got 55. Oh, it's a left Riemann sum, sorry. Done so many trapezoid sums, I was starting to do that. And then the next rectangle, 9 minus 4 times the left side, 57.1, plus 15 minus 9 times the left side, 61.8, plus 20 minus 15 times the left side, 67.9. Okay, so that's my value. Does this approximation overestimate or underestimate the average temperature of the water during these 20 minutes? Well, first, if you do take this further, you should end up with 60.79 degrees Fahrenheit is the average, is approximately the average temperature on 0 to 20 minutes. But then they ask whether or not this is an overestimate or an underestimate. So let's go back and think about, they told us in the stem of the problem that this is a strictly increasing function. So here are some increasing functions. And now let's think about the LRAM that we just did. We just did an LRAM. In fact, let me spread these out a little. And so we went to the left side, the left side, the left side. Well, our sum is an underestimate there, and with concave down, we go to the left side, we go to the left side, we go to the left side. Again, I get an underestimate. So this approximation is an underestimate because LRAM produces underestimates for increasing functions. And you might want to stick in strictly increasing functions or always increasing functions. Okay, so that was part C, and then finally part D. Part D says on 20 to 25, W models the temperature, has the first derivative, a W prime equals 0.4 square root of T cosine 0.06 T. Based on this model, what is the temperature of the water at time equal to 25? Okay, so we know the temperature of the water at 20. So I think if I integrate from 20 to 25, W prime, that should be W at 25 minus W at 20. So if I do this integral and add W of 20 to the value of that integral, I'll get W of 25. So this was 71 plus the integral from 20 to 25, W prime dt equals W of 25. And I integrate and add 71, I end up with 73.043 degrees Fahrenheit. Okay, there's problem number 6. Let's take a look at problem number 7. Problem number 7 says zoo sponsored a one-day contest to name the new baby elephant. Zoo visitors deposited entries in a special box between 0 and 8. The number of entries in the box was modeled by a differentiable function e. Okay, e for entries. Nice. Use the data in the table to approximate the rate in hundreds of entries per hour at which entries are being deposited at time equal to 6. So I'm going to say that E prime of 6 is approximately E of 7 minus E of 5 over 7 minus 5. And so I end up with 21 minus 13 over 2, which is 8 over 2. And this is 4, but remember they told us this was in hundreds of entries per hour. So 400 entries per hour approximately at t equal to 6 hours. Okay, part B for number 7. Part B for number 7. Use the trapezoid sum with 4 intervals given by the table to approximate, don't forget that 1/8. The subinterval widths are not the same. I don't even know why we teach you that rule, that shortcut, because College Board never uses it. So we've got, oh, and we can pull out that 1/2 from all the trapezoids. So we've got 2 minus 0 times base 1 plus base 2. And then we've got 5 minus 2, base 1 plus base 2. And then we've got 7 minus 5 times base 1 plus base 2. And then finally, 8 minus 7, 21 plus 23. This is with calculator. You're welcome to go further. You're welcome to leave it here. If you did go further, you should end up with 10.688 hundreds of entries per hour. So 8, so approximately 1,069 entries per hour. During is the average number of entries per hour on 0 to 8 hours. Okay, I like that. Yes. Part C. At 8 p.m., volunteers begin to process the entries. They process the entries at a rate modeled by P. Okay, that's another rate function, so I'm going to be integrating that to get the total number of entries from 8 to 12. So that's midnight. From 8 p.m. to midnight, they're counting or processing these entries. How many entries had not yet been processed by midnight? Okay, so we need to find the total number of entries. How many entries are in the box at 8 p.m.? And I think the way I'm supposed to figure out that there are no. How many entries are in the box? Number of entries in the box is modeled by. Oh, I see. Sorry, just the brain shut down for a second there. So at t equals 8, e equals 23. So we know that there are 23 hundreds of entries in the box at 8 p.m. Okay, so that's how many we've got. And now they start processing. So we integrate that rate from 8 to 12. And we figure out what we get there. I got 1600 when I did that. And so how many are still in the box? 2300 minus 1600, or 700 entries still need to be processed at t equals 700. Oops, at t equals midnight. Okay, so this gets done on my calculator. I had to understand and interpret the meaning of that number from the table. That helped me out for a minute, and then simply subtract the two. All right. What's next? According to the model in part C, at what time were the entries being processed most quickly? Okay, so let's think about our processing function. P equals t to the third minus 30 t squared plus 298 t minus 976. So processed most quickly, I want to find when p prime equals 0. So p prime equals 3t squared minus 60t plus 298. And if I find the vertex of this parabola, minus b over 2a, I get 60 over 6, or at time equal to 10. At what time? At time equal to 10, which is interesting because that's not what I've got. Oh, I'm sorry, I'm looking for p prime equal to 0, not the max on p prime. Duh. See, that's why you write things down like this. We pull out our calculator and we graph p prime. So p prime is 3t squared minus 60t plus 298. Okay, and I'm graphing this on 8 to 12, and and I'm looking for zeros, so graph. Okay. Hundreds of hours, 8 to 10. Well, it looks like there's only this one place where p prime goes from positive to negative, and that's an indication of a max. So let's find that. So I can calculate 0. Enter, enter, enter. And I get 9.184. Okay. 9.184 p prime is equal to 0. Fabulous. Okay. So I've got 8, I've got 12, and I want to consider p of 8, p of 9.184, and p of 12. I want to do a candidates test here. Since I'm allowed my calculator, it's not going to take that much time. I just need to be careful about typing in this function. 30t squared plus 298t minus 976. Okay, and then I'll go to my table and I'll type in an 8 and I get 0, and I'll type in a 9.184 and I'll get 5.0887, and I'll type in a 12 and I'll get something I can't read. I'll get 8. I'll get 8. So it looks to me like this number is greatest. Was there a minimum in there somewhere? Does this come back up again? Did we miss something in here? Did I not type it in properly? Let's look at P. Graph of P. Goes up. Of course, it's going to go up really high, so I should probably change my viewing window. But I definitely want to... Oh, I'm only looking at 8 to 10. Oh. Oh. Okay. 9.184. Oh, and I still have p in here. I need p prime back again. So 3t squared minus 60t plus 298. Duh, it's parabola. Should have 2x intercepts. Why didn't one of you say something? Okay, graph. So that's the 9.184, but look, we have this one over here. And so we've got a max over here at 12 as well as a max here. And what about this other point? P of second, calculate 0. Enter, enter. And I end up with 10.816. Okay, 10.816. You know, I don't expect that number to be bigger than this one here. But because I expect a minimum, p goes from negative to p prime goes from negative to positive there, which means p goes from decreasing to increasing. So I expect a minimum there. But I'm doing the full candidates test, so let me get the value for that. I've got x to the third minus 30x squared plus 298x minus 976. Then I go over to my table and I type in 10.816 and I end up with 2.911. So I see the maximum occurs, max entries being processed is 800 per hour at t equals midnight. Okay. You know, not here where there was a max, but this was actually at an endpoint. So don't forget, maxes can occur at endpoints. And that was part D. And we're all done with number 7. Let's take a look at number 8. Number 8 says rate of fuel consumption is given by, in gallons per minute, is recorded for an airplane flight, twice differentiable, strictly increasing function R. So R is gallons per minute. Okay, that's the rate at which the plane consumes fuel. The graph of the table, the graph of R and the table of selected values of R on 0 to 90 minutes is shown above. Use the table to find an approximation for r prime of 45. So that's going to be approximately r of 50 minus r of 40 over 50 minus 40, which gives me 15 over 10, or 1.5 gallons per minute. Those were the values for R, remember? And on the bottom, we have minutes. Okay, so that's my answer to part A. Do they ask me to show computations, indicate units of measure? Great. B, the rate of fuel consumption is increasing fastest at time t equal to 44. That means the slope of r is most positive at time equal to 45. What is the value of r double prime of 45? Explain your reasoning. Well, if my function is always increasing to its fastest rate, and then still increasing but increasing at less of a rate, that's going to be an inflection point on r at t equals 45. So the max on r prime at t equals 45 minutes is when r double prime equals 0, given twice differentiable r. I'm putting this last statement in here because I don't want them to say, well, maybe r double prime is undefined. And I want to say no, because you told me that this was a twice differentiable function, which means r double prime must exist everywhere. Okay, so that's part B. Part C, approximate the value using a left Riemann sum. A left Riemann sum with 5 subintervals. Okay, so we want 0 to 90 of r of t dt. And we want a left Riemann sum using 5 subintervals. The subinterval widths are not all the same, so again, I can't use any shortcuts there. I'm just going to say that this is approximately 30 minus 0, and we're doing a left Riemann sum, so I want the first number plus 40 minus 30 times 30 plus 50 minus 40 times 40 plus 70 minus 50 times 55 plus 90 minus 70 times 65. Okay, that's going to be my left Riemann sum, and if we sum that all up, we get 3,700 gallons. Right, because we were doing gallons per minute numbers times minutes. So gallons per minute times minutes. These cancel, leaving me with just gallons. Gallons per minute times minutes gives me gallons. Okay, so what is that? That's approximately, is this numerical approximation less than the value, the actual value? Well, we're told that this is a strictly increasing function, and again, we're doing LRAM, and we saw that LRAM for strictly increasing function was always an underestimate. 3,700 gallons is an underestimate of the integral of 0 to 90 of r dt, because r is strictly increasing on 0 to 90. Okay, and you might want to, if you don't feel confident with that, or you don't feel like that's enough, you could go on to say, so LNAM produces underestimates in these situations. Okay, that was part C. Let's take a look at part D. On 0 to 90, explain the meaning of the integral from 0 to b of r of t dt. Well, isn't that the number of gallons consumed up to the bth minute of the trip in terms of fuel consumption? Explain the meaning of, oh, so this was number of gallons consumed to up to the t equal to b minutes of the trip. Okay, and then the next part says explain the meaning of 1 over b integral 0 to b r t dt. Okay, so that's going to be number of gallons consumed divided by number of minutes. And so this is going to be the average rate at which fuel is consumed in gallons per minute. It's the average value of the gallons per minute function on 0 to b minutes of the trip. Okay, and there we are. We're all done with this packet. Indicate units of measure. Yes, we have gallons, we have minutes, we have gallons per minute on 0 to b minutes. Fabulous. I hope this was helpful, and I look forward to taking any questions you have on it. Have a great day.